Hi, everyone. My name is, can you all hear me? My name is Chetan Nayak. I head the quantum hardware program at Microsoft, and I also have an affiliation at the University of California, Santa Barbara, and also with the Quantum Science Center, which is one of the 5 DOE NQI centers. Moving on to the next slide. I was asked to talk about the biggest challenges. I see a number of challenges on both the hardware and software side towards realizing utility scale quantum computers. We need high fidelity gates. So we need to be able to perform operations with our quantum computer with relatively low error rates. We need those gates to be fast because we want to be able to solve problems on relevant timescales. We need our qubits to have small footprints and to be low decoherence. We need a scalable readout and control strategy for those qubits. And on the software side, we need more high-value applications. We have some, but more is, I expect that we will discover more as we go along, and it's important to have more. In terms of what can be done about that, I think that we certainly need materials and fabrication process development in order to be able to hit the goals that I said on the qubit side. We need cryogenic infrastructure to be able to cool down a large-scale quantum computer and maintain it in a low-noise environment. And then we'll need classical control logic in order to drive a scalable readout and control strategy. The reason that we need all these things, if we move on to the next slide, is that when we think about what we could use a quantum computer for, there's really a maze of proposed applications based in turn on a zoo of quantum algorithms. There's actually a web page, Quantum Algorithm Zoo, one could take a look at. There's 50+ quantum algorithms with various kinds of speed up. However, if you take a look at those, and moving on to the next page, if we think about when and where will quantum computers be practical, they'll be practical, first off, for problems involving a small amount of classical information in order to state the problem, but needing large computing resources. What that in turn means is that if we think about early error-corrected quantum computers, because quantum computers, like classical information, cell phone information, or satellites, will require an error correction infrastructure, early error-corrected quantum computers capable of solving valuable problems will have 1,000 to 10,000 logical qubits, which is probably 100,000 to 1 million physical qubits. Just to put that in perspective, we currently have somewhere the largest quantum computing machines have 50 to 100 physical qubits. So we do have a long way to go, and new problems arise as we reach that scale. However, for those numbers to be within the realm of possibility, we're going to need all the things that I said, which is we're going to need relatively low decoherence qubits with a small footprint. By comparison, of course, classical computer CPUs have billions of transistors. So although it looks like a large number, there are ways in which it's not such an outlandish number. Looking now at the resource requirements for various applications, the earliest things will be what I call academic quantum advantage, which is solving interesting scientific problems that are not necessarily immediately practically relevant, but proven principles that otherwise unsolvable real world problems can be solved, and they'll require 100+ logical qubits. And if the ratio between physical and logical qubits is something like 250 to 500, then you can multiply through and get into the thousands of physical qubits, or tens of thousands of physical qubits, sorry. Code breaking would be the next. That's in the 10,000 to 50,000 logical qubits, again, required for those kinds of applications. Moving on, chemistry simulations, quantum chemistry simulations, such as the design of new catalysts that could be potentially relevant for carbon capture or nitrogen fixation. That's sort of 14,000+ logical qubits. And then finally, material science applications, as was mentioned earlier, for instance, for designing or helping to discover new superconducting materials. That's in the 100,000+ logical qubits. So as you can see, what we need to really solve valuable problems is hundreds plus, probably thousands or more of logical qubits. And in order to do that, we are really going to need sustained development on fabrication, materials and fabrication process development, cryogenic infrastructure, and scalable readout and control logic. So thanks very much for your time and attention.